Science 757, Polymer Rheology, Professor H.H. Winter, Lecture 4A. The abstract formulation of strain measures should be related to specific experiments, and that's what I'm trying to do today. I will go through a few examples with you. Remember, we looked at the blowing up of a balloon. And on the balloon, I drew some lines, and these lines are increasing their length during the blowing up of this balloon. And note that those lines are very long. They have some curvature due to the curvature of this balloon. Now, the question is, what is the strain tensor which describes the blowing up of the balloon? Schematically, the balloon is drawn here on the blackboard. Here, this is supposed to be the balloon blowing in the air. There's some pressure inside which is higher than on the outside, and the characteristic strain variable is the radius. Now, the skin is being deformed during the blowing up, and we will draw now two infinitesimal material vectors into the skin. One vector being tangent to the skin, this would be in one direction. The other one, second, also would be tangent in the skin. This would be our 2 material vector. And 3 would be normal to the skin. This would be E3. Note that I'm using large vectors, but I really mean a small material element here. So this is an infinitesimal material element in comparison to the large material element I'm using here for drawing the curved streamlines. So the first important thing to notice is that the material vectors in the infinitesimal material element remain straight. They are not curved, and that's one reason for going to the small element. So we take a small element in here, and we would like to know now what are the stretches in all 3 directions. The stretching in one direction, this is the stretching down here, is associated with the circumference of the balloon, and it's given as the ratio of this length at time t divided by this length at some previous time t prime, and that's given as the radius ratio at time t and t prime. So the stretching is associated with the instantaneous radius. Now, the second material vector coming out of the board is symmetric. It has exactly the same property as the first material vector, and L2 is equal to L1 in this case. L3 is the material vector coming out in the board, out of the skin. Now, the skin is decreasing its thickness as we are blowing up the balloon. Therefore, with conservation of mass combined with constant volume, combined with constant density, we can say the volume is conserved with L1, L2, L3 are equal to 1. The product of those 3 is equal to 1. And since we know L1 and L2, we can formulate now the stretching in the third direction in terms of the radius change. So those 3 stretches are identified. We also could look at the extension rate, which is given by this expression, the change of radius divided by the instantaneous radius. And you can check if you put this extension rate into the formula which we derived before for stretching in one direction, then you can check that this L1 is equal to the formula which is given here. With this result, we can now go to the strain tensors which we calculated before, which we calculated in class. The flow associated with blowing up of a balloon is extensional flow. In this case, it's biaxial extension because we're stretching in one direction and equally in the 2 direction, and it's shrinking in the 3rd direction. So that type of flow is a biaxial extension. And if you would look at the velocity field here, I have this in front here, the velocity field has an extension rate in one direction which is equal to that in 2 direction. That's the one you saw before on the blackboard. And the extension rate in 3 direction is accommodating conservation of mass. You can calculate from that. So that's fully determined. The velocity gradient, this is an independent handout which you got. We will use that several times when going through those examples. So I accumulated all the standard formula which we derived before. Those are the formula for extension flow. This is velocity gradient. This is the stretching in the 3 directions. And from those stretches, L1, L2, L3, we get the component of the deformation gradient, of its inverse, and get the Cauchy tensor and the finger tensor, and everything is solved. Let's look at a second example, and that example is fiber spinning. We have a material being extruded out of a small hole, and so a little thread is coming out of a hole, and then this thread is being pulled at very high velocity, so it's increasing its length, or it's shrinking in diameter. The schematic of that film of this fiber pulling experiment, a fiber spinning experiment, is shown here. This is the little thread, and in the moment, let's assume that we are talking about an axisymmetric fiber spinning experiment. So everything would be determined by the radius at 2 positions. But let's look at a material vector which is somewhat in an angle here. Let's say some segment of a molecule, or maybe an enclosure. And this material element, this segment, this material vector is being rotated and stretched when it goes from the upper position to the lower position, when it goes from state T prime to state T. And the rotation and stretching of this vector is given, raise this up, the rotation and stretching is given by the deformation gradient between T prime and T. If we have that deformation gradient, then we can calculate all those components. And you can do this as an exercise, determine the deformation gradient in a fiber spinning experiment. But I wanted to go through this manipulation. Assume that you know, say, R prime, and you also know F. The question is, what would be R? You want to know what's the stretching and what is the rotation of this material element. So we assume in the following that we have the component of F. The experiment can be evaluated in the following way. We measure the radius of the fiber at position where it's at R prime, and at the position associated with state T. We calculate the stretching from the decreasing of the radius. That gives us the stretching in 2 and 3 direction. If 1 direction is the dimension in fiber direction, and 2 and 3 are directions perpendicular to that fiber direction. So they would be in the plane, in the cross-section of the fiber. So L2 and L3 would be decreasing with the radius. We assume a homogeneous deformation, assume symmetry in that case. And then with the assumption of constant volume, we are getting the stretching in 1 direction. From the radius change, we have all components of the deformation gradient. And now we can examine the different components of the incremental material vector which we drew into our fiber. We want to know the components of those little vectors here. And we need 3 components, obviously, to describe those vectors fully. Okay, so let's look at component 1 of R prime. And that's given as R prime dot delta 1. It's just multiplied with a unit vector in 1 direction. That will give us the 1. This is a scalar product, and the result is a scalar. So R1 is a scalar component. And that's defined with R dot F. That was our definition. R prime is R dot F, multiplied with delta 1, with our unit vector in 1 direction. Now, in component notation, we can express R as the summation of Ri delta I, where I goes from 1 to 3. I want to specify that notation just once with you. This is just to give you an example for the notation which is used by Bird, Armstrong, and Hasaga in their book. So vector R is represented by Ri components multiplied with a delta I. Those are the 3 unit vectors of our base. And we are summing up now from I equal 1 to 3. Multiplied with F, and F is given by the components Fjk, multiplied with the dyad delta J delta K. And we're summing up from J equal 1 to 3 and K equal 1 to 3. And all of this is multiplied now with delta 1. Note that there is a scalar product between delta K and delta 1. Now, if K is equal to 1, then this scalar product is equal to 1. It's just unity. It has the magnitude of 1. If K is equal to 2 or 3, then it denotes vectors which are normal to delta 1, and the result is 0. So only if K is equal to 1, we have a contribution to that equation. In the same way, we look at the dot product delta R and delta J. Those are unit vectors in different directions, and the dot denotes a scalar product of the two. And this scalar product is equal to 1 if I is equal to J, and it's equal to 0 if I is different than J. So the only contribution to that term here comes if J is equal to I. Therefore, we can rewrite this term with the summation into this simple form, saying I has to go from 1 to 3, and we are forming the product then of Ri, Fi, K, and K has to be equal to 1 because delta 1 and delta K in scalar product told us that K is only contributes if it's equal to 1. So I put in the red one denoting this multiplying with the 1 component. Or in a regular writing, I would say R1 times F11 plus R2 F21 plus R3 times F31 is the result. That's the 1 component of R prime. The shorthand notation for this is written below. It's obvious that I has to be summed up from 1 to 3, so we leave out the summation notation, and we just write down now the scalar value of R1 prime is equal to Ri Fi 1. And this means that we are summing up over I over 1, 2, and 3. And you can do that with the given components. Interesting in this experiment, when you look at those components, is the following. You could take a vector R prime, which might be a diagonal of a cube in the beginning, and then when you stretch your material element as the fiber is being stretched, then this vector is elongated and it's rotating. The flow is called irrotational flow, but still material elements in that flow, when they elongate and when they change their dimension, they require angle changes for those little material lines. And that's really the reason why the molecules in fibers are highly oriented, because the segments of the molecular chain are also oriented during that fiber spinning process. Another example, which is very common, is flow-through pipe. Let's see how can we formulate the strain tensor for flow-through pipe. You're pushing some liquid through a pipe, maybe a circular cross-section in this direction. This would denote the velocity distribution. It's parabolic for Newtonian liquid, or has some parabola of higher order for shear thinning liquid. But basically, that's the type of velocity profile. We are looking at 0 velocity at the wall, maximum in the center. A material element at some finite radial position will maintain that radial position and just will move along in z direction as we look at it at different times. Now, this material element is, again, an infinitesimal material element. It's very, very small. So let's focus on that point for a moment. The velocity gradient is giving us the shear rate, or in other words, the angle change per time of this material element is given by the local velocity gradient. Now, this velocity gradient is 0 at the center of the pipe, and its maximum at the wall in its magnitude. The flow is an inhomogeneous flow. A line which you would draw across here would be curved very soon. So only an infinitesimal line can be described as a straight line at different times. And that's what I mean here when drawing those two states of our infinitesimal material element. We can, for describing the strain of this material element, we can use the method of Lodge now. Lodge suggested that at time t, you would pick a material coordinate system, say, 3 material vectors which are of unit length and which are at right angles. You just assume that you're drawing this into the material. And then at some preceding times, those material vectors had a different length and different angle with respect to each other. Now, the material vector E1 turns out to be the same at previous states because all material points on this material vector E1 move at the same velocity. So this vector is not being stretched. A material vector E3 is a vector which goes in hoop direction. If you take this material element here and associated this with a ring element, then this would be a vector in 3 direction, and that the radius of that hoop element stays constant as the material element moves along a path of constant radial position. So E3 is the same at the 2 states, at T prime and T. The only interesting material vector is really E2, which is in some angle at previous times, and it also is associated with some stretching because of the angle change. Now, it's an angle forward, tilting forward here, because the velocity gradient is negative, the shear rate is negative. See, when you look at this material element up here, the bottom part is moving faster than the top, and that will install the rectangular configuration at time t. The components now of our 2 systems are given down here. At time t, we have an orthonormal system, so we have 1, 0, 0, and 0, 1, 0, and 0, 0, 1, as defined, as chosen specifically. Now, at time t prime, E1 is also given as 1, 0, 0, and E3 is nothing specific, but E2 had a 1 component, which is minus gamma, and it had a 2 component, which is equal to 1. And this value of gamma is really given through the definition which we used before. It's the integration of the shear rate. And shear rate here is the shear rate is given by the velocity gradient, and we're integrating from t prime to t. Now, this shear rate doesn't have to be constant in time. It can be variable of time. You can have some transient experiment in pipe flow, and you still could describe your flow in this fashion. Now, having calculated all these components, we can go back now to the formula which we derived in class. We can look at the strain tensor and the deformation gradient tensor. Let's do that here for a moment. Velocity field for shear flow can always be reduced into this format. You could say a shear flow is a flow for which you can find a coordinate system which reduces the velocity field into those components. You can choose other coordinate systems and describe shear flow also, but then the components will be more complicated. So in all cases, we can reduce the kinematics into this format. It would be basically a velocity distribution as sketched here. The velocity gradient has as the only parameter the shear rate, gamma dot, and with the shear rate, we calculate the shear strain, introduce the shear strain in the deformation gradient, in the inverse, and from that we calculate the Cauchy tensor and the finger tensor, and all results are there. The strain for a material element in pipe flow is completely defined. Okay? And the kinematics, the velocity field, will enter through the rate of deformation, enter through the shear rate as shown here. Now I will use those formulas maybe in some later applications, so let me keep those outside, because they will be the same for shear flows and extensional flows, whatever we are going to look at. Here I have another example which is quite common in the rheology laboratory. And I brought you the hardware, the fixtures associated with this. Maybe you can see this on the screen. The sample is put between two concentric disks. So the axis of the two disks is the same. And we are putting a small sample in between. And then we are rotating one of those disks with respect to the other. We are introducing a deformation in the material. And our objective in class now would be to calculate the finger strain tensor and the Cauchy tensor for this type of deformation. And note that our material elements are moving on curved streamlines, so we have to look at the effect of curvature. A experiment. Let's look at the kinematics in a moment in further detail. So the sample is between two disks, as shown here. We choose a coordinate system with radius r, and z would be the axial direction, and then there would be a circumferential coordinate, would be theta. It's a so-called cylindrical coordinate system to describe the flow. And in that coordinate system, the velocity components would be 0 in r direction, 0 in z direction, but it would be finite in circumferential direction. So those particles, material particles, in our sample move on circular path lines. They don't move up or down. If we have some secondary flow, if the experiment goes wrong, they might move all over. But we desire, for a well-defined experiment, we would like to have circular streamlines for our material particles. The shear rate in this case is given by the relative motion between the top and the bottom plate, and that motion divided by the spacing, h. So we would have the top plate moving at the velocity r, would be a local position here, r, times the angular velocity of the top plate. That's what our motor, the drive, will give us. This omega is a function of t, divided by spacing h. Note that the shear rate is 0 as r is equal to 0, and its maximum at r equal to capital R at the outer edge. So there's a linear increase of the rate of deformation. It's again a non-homogeneous deformation. And if you would draw a line, if you would take this type of fixture and would draw a large line in here, that the outer edge of that line would move at a different velocity than the inner point of this line. In this case, actually, it would stay radial because it would accommodate just the shorter path at the inner, at the shorter radius, and would accommodate also the longer path at the outside. So that's where what we are going to look at now for a specific material element. We in an experiment, for instance, we we mounted little particles between two halves of our sample. We have just two little disks. I didn't make a copy of that, but you can imagine. We have just two little disks being molded and then small particles in there. And then the two are sandwiched together, so those particles are in there. And the flow starts, and those little particles are deforming during the flow. And the deformation is something like this. Here it's maybe we start with a spherical particle, and that particle is then elongated into some ellipsoid. Note that it will be just getting longer due to that shearing deformation, but the width is about the same. So it's not an axisymmetric fiber which we are producing. It's more like a linguine. It's like a flat noodle which is produced in that type of deformation. Now, let's look at the deformation gradient for this specific experiment. The material element is moving on a curved streamline. This is supposed to be the path it's moving along. Again, it's an infinitesimal material element, very, very small. And the characteristic of that is that the straight material vectors remain straight because we're just looking at such a small dimension. The material vector, for instance, E1, we are picking that tangent to our path line, is tangent at some later times, and it will be rotated. It will first be directed like this, and then it goes like this, and then in the back of our rheometer it comes around. So it's really rotating while time goes on, and then after a while it comes back to this position again. Now, the velocity is constant along that streamline, so the length of E1 will stay constant while it's being moved around. To analyze the flow, I'm again using Lodge's approach, picking a set of orthonormal material vectors at time t. So they are of unit length and at right angles. The question is, where have those material vectors been at some previous time t prime? Now, for a very small material element, this vector E prime E3 is just going in radial direction, and it will be radial in both states. The flow is 0 in radial direction, so there's no stretching. So E3 doesn't change its length in those cases. I'm just picking convenient choices. You can pick any three material vectors to describe the flow, and you might as well pick the most simple ones, the ones which you can describe most easily. Sticking out of this plane where kind of nothing happens is the material vector E2, and that's again exposed to the shearing motion. It will be subjected to an angle change and will be subjected to some stretching. And this is being described with a shear rate. Remember, we had calculated already. For this case, we had already calculated the shear rate. It's given by the relative motion between the top and bottom plate divided by the spacing. So that shear rate now is introduced. Here it's r times omega divided by h. R and omega stay constant. This particle will move at a path line of constant radius. And we're just integrating from time t prime to time t and get the total shear strain in that experiment. And again, we enter all those results in the previous formulas as discussed before for the deformation gradient, inverse, Cauchy tensor, and finger strain tensor. So you're an expert now in, yes, question?
So then I'm not sure what it's called, basis comes out looking similar to the flow in the pipe. Is that right? Except with a different shear rate.
The question is whether this material base, these three material vectors, are coming out about the same as in the example where we looked at flow in the pipe. And the answer is yes. Both are shear flows, and the description in both cases is the same. We use the same formulas. We have everything reduced to one parameter, which is the shear rate. The shear rate is actually in both cases a function of position. In pipe flow, it's a function of radial position. And for the concentric disks, again, the shear flow, the shear rate is 0 at the center, maximum at the outside. So again, it's a function of radial position. Here, it's a linear function of radial position. For pipe flow, it's a more complicated function of radial position. But both are shear flow, and the formula for describing the shear flow are exactly the same. And that's really the point I'm trying to bring across here. We look at a flow here in between the plates, a very complicated flow which has lots of curvature. And the approach is exactly the same. Those material vectors are not affected by the curvature except for their change of rotation. You know, E1 has this direction and it has that direction at some later time. So the material element is rotating in the flow. That's what curvature does to that in this example. But otherwise, our three linear material vectors are described in exactly the same format. Later on, we will look at the stress tensor, the components of the stress tensor in curved coordinate systems. And then we will apply forces on a curved surface. And there's a difference. Now you will see that when we look at the stress tensor components. But for the strain, curvature has no effect on our description here with this material element. And that's actually one reason why I prefer Lodge's approach, that we draw this type of material vector and this material coordinate system to describe the kinematics. You could describe the kinematics with F being differential operator, operating on the motion. And there, curvature comes in, or time derivatives are very complicated to incorporate curvature. If you use that approach, everything comes out naturally, and you get your result with the least amount of mathematics. So I hope you see that when going through those examples. That's an objective I would have with that formalism. Yeah, question?
You said the E3 prime is vertical to the E1 prime?
Yes, E3 prime at time t. The question is whether E3 prime is normal to E1. Is this? It is also vertical to it at this time, because we're talking about an infinitesimal material. Well, no, even if in the experiment we have basically here, if you look at the experiment here, we have layers of material which move across each other rigidly, like disks in a record player. They're just rotating at different speed, but they are moving rigidly. So if you have, say, if you have a disk like this and you draw a line in 3 directions, that line will rotate rigidly to its new position, and it will not change its angle. So E1 and E3 are not changing their length or angle. Because of that specific geometry, yes. You're talking about the specific geometry flow between concentric disks. Yeah. Yes. Okay. So now you're expert. Let's look at a more complicated flow. Another experiment. It's actually the more simple the experiments are, the more difficult they are to analyze. So let's take a very simple experiment. We just have a flow going through contraction. It's a plexiglass tube which changes its radius, its diameter, as we go down here. And on the top, we mounted a wire. There's a polymer solution in there, but that's not the important point I want to make. We have a little wire here, and it is acting as an electrode. There are parts of this wire being exposed freely, and when we run a current through this wire, we can produce bubbles, and those bubbles are used then as a marker. So bubbles are produced, and then at some time later, the bubbles are here. Now, we don't produce bubbles constantly. We do that like Indians give smoke signals in the movies. You know, we just release bubbles occasionally. So we have bubbles like this, and another burst of bubbles, another burst of bubbles. And the residence time of those bubbles is changing in time. Let me draw some frame around those. This is the set of bubbles which just has been released. This is at a later time, an even later time, and even later time. You can see that the burst of bubbles is elongated because it's a flow which has acceleration in there. And the angle is changing because we are shearing. There's a shearing deformation of this material. Now the question is, how can we describe the strain tensor in that type of flow using the same framework which we used before? Schematically, we describe the flow in a cylindrical coordinate system. A material element upstream, say when the bubbles are just released, would be such. Here would be a square material element, and at some later time would be something like this. Now, remember how do we describe a flow? We need 3 independent material vectors for a complete description of that flow. Let's pick A1, a material vector in one direction, A2, a material vector in radial direction, and then A3 would be a material vector in hoop direction. If we know A1 and A2, then we can calculate A3, or vice versa. They are connected by conservation of mass. Now, it turns out that A3 is very easy to get. It's associated with the radial position. It's associated with the ring element here, and as the radial position changes, the hoop length is decreasing here, for instance, and in this case, A3 is shrinking. So we should measure the radial position to get A3. The method of large, picking a material coordinate system at time t, which is orthonormal, doesn't work here. We are not free to choose that material coordinate system. We just get as much as we have available. We have, for instance, at time t here at some later time, we have the most distorted element. We have A1 and A2, and we can measure A1. We can measure its new length. Before it was, say, length 1. We can measure the new length of A2, and also can measure the angle of A2, and then we get 2 more parameters, B and C. Those would be things we measure from our experiment, just optically. We take that. And A3 would be given to us by the radius change, which we are also going to measure. So let's assume that our measurement gives us A, B, C, and also R and R prime for our material vector. Question is, what's the finger strain tensor, what's the Cauchy tensor, and what's the deformation gradient in that type of situation? And it requires a little more work. We will be able to calculate the components of the deformation gradients from the 3 equations. We take our first material vector, A1, at 2 states, prime and at time t, and multiply this here with F, and this is our first equation. We do this with the second material vector and the third material vector, and know that our material vectors are given for the 2 states. We know that from the experiment, and we want to calculate F now. Let's start with equation 1 of this plot. Equation 1 is an equation for a vector. It's a vector equation. I could write it down in components. You can see that this vector equation really is consisting of 3 algebraic equations. You would have 1 is equal to some term which comes out of a manipulation between those 2 matrices. Okay? Now, before I did that manipulation with you, and we went through all those summations and came up with this so-called Einstein notation. We would say the 1 component of this equation here, the 1 component here, we have 2 subscripts. subscript 1 denotes our first material vector. So denote this as just a vector, material vector here. And we have the one component of that is equal to that vector at some time t, taking the ith component, multiplied with fi 1. And this 1 comes, if you remember this, we dotted here with delta 1 to get this component in the previous example. Or if I don't use the Einstein convention, if I write the three components, they are given as such. And remember now, we know the three components of A1. Let me go back to this previous case here. This was our material element at time t. And for our material vector A1, we know that it has components A0, 0. And we introduce those now into our equation. A times F11 plus 0 times F2, F21, plus 0 times F31. And our result is F11 is equal to 1 over A. The first component of our 9 components is determined. The second component now of this equation on the top will be given by multiplying this equation with delta 2. And we end up with now the 2 component of A1 prime is equal to A1, taking the ith component times Fi2. Again, the 3 components. So I goes from 1 to 3. We have the 3 components. And we remember that we remember that the 2 component, one moment, what do we need? We need the 2 component. We need the 2 component of A prime. The 2 component is 1. We know that. And, no, excuse me, the 2 component is 0 of A prime of the first material vector is 0. And we need the 3 components of that material vector at time t, and this is A 0, 0. Again, A 0, 0, same components. And the result is that F12 is equal to 0. Let's try it again with the third component since I mixed it up so much. Let's take the third component. We get the third component of this vector by dotting with delta 3. And this results that we have A1 prime, 3, that's a scalar component in the 3 direction of our first material vector, is equal to this material vector at, this is A1, at time t, at state t, taking the ith component, and we're multiplying this with Fi3. We're summing I from 1 to 3. We get the 3 components. And on this side, again, we put in the 3 components of our first material vector at state t, A0, 0. We put that in. And we find that 0 is equal to F13. And this is the next result. You realize it's already hard work to get to all those components. Now, we have 2 more equations to do that. We have the equation for the second material vector. And again, we get 3 terms coming out of that. The second material vector is really the interesting one in terms of stretching and shearing. So that has the stretching components here coming in. And that's why F21 is getting minus B over AC, as you will see here. And then it has another contribution here just for the stretching. And we're getting the equivalent now for the third equation. We get 3 more components for F, and the result is really this matrix. For F is 1 over A, 0, 0, minus B over AC. This is, remember, B gave us the angle change, and C gave us the stretching of the second material vector. Here, C again gives us the stretching of the second material vector, and R prime over R gave us the stretching of the third material vector. And you have all the detail here, and with that information now, you have having the deformation gradient tensor, you would go into the equations as we had before. I'm using the equations where components are already filled in. You would look now at the Cauchy tensor being F times F transpose, and you would calculate those components, which is a little more work and looks a little more fancy, but you could do that very easily. and then you could do the inverse, and you would get the finger strain tensor. And as a result of all this calculation, you would have the strain tensor components of a very complicated flow field, which we produced in the laboratory and which we visualized in that case. So you can transfer the information you get from the experiment into a mathematical format, and you will need that mathematical format to calculate stresses and relate stress and strain maybe in a rheometry experiment or in an analysis of that flow. Maybe you want to look at flow-induced birefringence. You want to know the stress levels and the strain levels associated, and then you need this type of analysis. The strain rate for shear flow. Remember, in shear flow, we had as only parameter, we had the rate of deformation, which was associated with the velocity gradient. Now, that shear rate might not be constant, might be time dependent. There are actually many interesting experiments where we look at transient behavior of materials in shear. The system is at rest, and then we start the shear flow. In elastic liquids, there are interesting memory effects which we would like to analyze in this case. So let's assume that our shear flow, say maybe a material element in a rheometer, being exposed to that shear flow. So let's assume that the shear flow is 0, shear rate is 0 up to time t, and then we go to a new rate, and that rate stays constant. And the question is, what's the total strain between some time in the past and the current time t, where we, for instance, want to calculate the stress? That would be the instant of observation, and t prime would be some instant in the past. Now, if this is an instant in the past where the material is, say, at rest, if t prime is smaller than 0, if we are down here, then we would evaluate this integral by putting in the shear rate of the first part of the experiment. The shear rate would be 0 when we go from t prime up to t. When we integrate from t prime to t, would be no contribution. And then it would be finite, or would be constant in this case, when we integrate from 0 to t. Now here it is constant, we can put it outside, and the total shear strain, which is applied to this material element between some time t prime here and current time t, is equal to the total strain of this experiment. It's just t times gamma dot 0. Okay? Now, if we have a if we select an instant in the past during the period of flow, set t prime is bigger than 0, then we just integrate from t prime to t, and we get the shear rate multiplied with this difference t prime minus t minus t prime. We get this product as the total strain for the material element from here to here. So this formula looks slightly different to that, describing either the deformation from some time in the past to current time t, or from some time in the near past to current time t. And this then, again, this time-dependent formula can be introduced into the finger strain tensor, the deformation gradient tensor, inverse Cauchy tensor, and finger tensor, and then gamma will be just a function of t minus t prime, depending on the two states you're looking at. There's no change in the formalism when you look at transient flows or when you look at steady flows with that type of approach. Now, some people love the purely mathematical approach to calculating deformation gradients, and that's fine. That is on an equal footing to the approach looking at specific material lines. So I would like to go through an exercise with you where we look at a motion we will look at a material point P at time t prime, which moves along a path to its new position P at time t. So this is then denoted with this material vector x at time t. So the same point at two positions. Now, I'm doing this for a very simple flow. I'm using shear flow, where material paths are parallel to the one direction if we choose that type of coordinate system. Okay, so the material is just moving along the one direction. And we would like to evaluate now the components of the deformation gradient by saying the following. A neighboring point to P, say like some point Q or so, whatever you want to call this point here, neighboring point, would be separated with a small vector dx at time t. At a preceding time, this same point would be over here, and it would be separated from P by this small material vector dx prime. So the characteristics of the flow really will tell us or will give us the relation between dx and dx prime. It's just a characteristic of the motion in the vicinity of point P. For shear flow, we can express the vector x prime in terms of the position vector x, because we know the kinematics. We could say the position vector has the one component, the component in one direction here, at the prime position, which is, so has, that position is equal to its position at time t, this would be x1, minus the distance it traveled, and that's given by its velocity and integrated from t prime to t. So that's the distance the material element has been traveled over time t prime to t. Now, this velocity is given, in shear flow, this velocity, let me remind you on our components here. This is for shear flow, we have gamma dot times x2, that's our velocity component in one direction, which we are going to use. So we know the velocity component in one direction. It depends on the x2 position and depends on the shear rate of our experiment. Let's say we know the shear rate. So x2, the position in two directions stays constant during this deformation. We can pull x2 outside. And we just know that now that x1 prime is equal to x1 minus the path, which is x2 times gamma, the total strain in that shear experiment. The component in two direction of this material vector, the component up here, stays the same because the material is moving at a path which has a constant distance in two direction. And also in three direction, there's no motion. So the prime and the t state are identical or giving identical components. Now we are introducing those components into our notation for the deformation gradient, and we calculate the one component, one component, 1, 2 component, 1, 3 component, all those components, taking the derivative. The interesting part is maybe f21 component. We take the derivative of x1 prime with respect to x2, and this will give us minus 1 times gamma, so this is minus gamma. Or if we take the two component, we take this derivative, this component, dx prime 2 with respect to dx2, and that's equal to 1. And in three direction here, similar component. Those are the stretching components, which doesn't amount to anything. We know that there's no stretching. And these components then result in a deformation gradient, which we have here. Okay, this is the deformation gradient. And we introduced the deformation gradient again in our formalism for the finger strain tensor, and we are on the Cauchy tensor, and then we have the same result as before. So both approaches are consistent. this concludes what I want to say about the strain tensor. I hope you got some feeling of, because you have to do some examples yourself. You have to try out, and you have the handout to do that. So let's break at this point and then move to a new subject. Rheology, Professor H.H. Winter, lecture 4B. The counterpart to the strain is the stress. So we should define forces in a deforming material. We calculated already the forces associated with blowing up of a balloon, if you remember, as somehow the tension in the skin was associated with the pressure. And certainly it's associated with the deformation of that balloon. In a very general way, I drew an experiment here. Let's have a lump of material being squished between two surfaces. You know, just have two solid surfaces approaching, and you're pushing on this material. And there's certainly some stress in this material. The question is, how do we describe the stress in this material? What would be the mathematical formalism? And what would we like to know? We would like to know the stress at every position in this deforming material. The stress might not be the same. So we would like to look at this distribution of stresses. And then we also would want to describe the stress in terms of forces. Forces we are kind of used to, but stress, what's the stress tensor? Let's stay with forces in the moment. And we could measure forces, say, in the material by cutting the material here and introducing this magic transducer. Let's say we have this very flat transducer which we can sneak into the material at this small area dA. And the direction of the transducer would be n. N is a unit normal. Now the transducer would measure the force which is transmitted through this little area. And that force, if we call this dF, that would be a vector, would have direction and magnitude. And this force would be bigger if we look at a bigger transducer, if dA is being changed. So by normalizing the force with the area of our transducer, we talk about the force per unit area and call that the traction. And for defining the traction, we would take, again, an infinitesimal material element. We would say dA goes to 0, assuming continuum conditions. We would not go on molecular scale. So that is one of the applications of the continuum assumption again. So the traction on our little surface is defined here as T if we know F. And we really would like to know, now to rephrase our question, we would like to know the traction at every position in space, but not only at every position. We can change our transducer now so that n wouldn't point in this direction. Maybe it would point in that direction. Or we really can choose any direction of this traction vector, of this dA, of this unit normal, and we would get the traction associated. And this traction now, if let's say we know all the forces locally, we have this transducer, we can measure everything. This traction would be given as a tensor, the so-called stress tensor, which we have to work with, which we have to define in greater detail, multiplied with the normal. The normal n is really defining our material, this area element in the material, this area element dA. So this is the defining equation now. The traction is given by the normal vector, which is then transformed into a new vector, stretched and changed in angle by multiplying it with this operator, with this stress tensor, to obtain then the local traction here. The stress tensor transforms as an operator n into t. Okay? And it's a tensor which has 9 components, which we have to look at greater detail. Now, how much information do we need to calculate the stress tensor P? Now, this stress tensor has 9 components, and you can see, as I was plotting this in this example, if we choose 3 cuts, say a cut with a normal vector n1, and a cut normal vector n2, and n3, 3 cuts, with the associated tractions T1, T2, and T3, if we know all this and introduce this information into our defining equation of the stress tensor, then we have, of course, 3 equations. We have one equation for our first area element with the first traction, and that first traction is given with 3 components. And we have 3 equations here, basically, to calculate 3 of the components of pi. We have another 3 equations with the second traction, another set of 3 equations for the third traction. And these 3 equations, these 9 equations are sufficient to determine the 9 unknown components of the stress tensor. So that really allows all the manipulation. And note that we can choose any 3 surfaces dA. We can choose any 3 linearly independent traction vectors and have all the information. For convenience, we will not use arbitrary traction vectors. We will use a more simple format. We will pick planes which are normal to the coordinate. For instance, at point P in our material, we could draw a little area element with a normal in one direction. We would call this a one plane. And the normal of that plane is identical with delta 1. Note a little vector like this is defined by its length and its direction, its unit length in this case. And it is independent of its position. So this vector is really identical with that vector. Okay, so those 2 are identical. And associated with that normal is a traction, and we would call this the traction vector on a one face superscript 1. Okay? And we can do that for all 3 coordinate faces. We can do this on a 2-face and a 3-face. On the 1 face in component, you have this first traction vector is given as delta 1. See, n is equal to delta 1 times the stress tensor. And that gives us the components pi 1, 1, delta 1 plus pi 1, 2, delta 2 plus pi 1, 3, delta 3, those 3 components. And you can see now that when writing the components of the stress tensor, that in this matrix, the top row really contains the 3 components of the first traction vector. And if you write it down in components, the second row, the middle row, is giving you the components of the second traction vector, and the same thing for the third row. So if you have the traction vector, coming back to our previous example where we picked 3 traction vectors to define the stress, if you have the traction vector, the traction vector on a 1 plane and the traction vector on a 2 plane and also the one of a 3 plane, you automatically have all the components of the stress tensor without any further work. Right? So the stress tensor components now have a meaning. The first 3 components are associated with a specific traction, and the other ones too. So they have those components have a physical meaning, and please keep that in mind when working with the stress tensor components. you can say now, then when looking at the subscripts here, so for instance, pi 2, 1, the two subscripts, what would be the meaning? The subscript 1 here is the second subscript, indicates the direction of the traction component. And the first subscript indicates the surface on which the traction is operating. In this case, we are talking about there's the 2 surface, so we have pi 2, 1. That's the one component of the traction on the 2 surface. Pi 2, 2 is the 2 component of the traction on the 2 surface. And pi 2, 3 is the 3 component of the traction on the 2 surface. Yes?
Doesn't that notation vary? In other words, as to which one is the traction vector or traction portion, and which one is the basis?
You're asking about, actually, could you rephrase it? I don't know why it should vary.
It seems like I've seen it where it just hadn't switched around.
Yes. Also, the question is whether the definition which we used for the traction here, traction being n times the stress tensor, is arbitrary, whether you should not rather use traction being equal to pi times n. It turns out that it doesn't matter, because the stress tensor, as you will see later, is symmetric. And the subscripts can be switched around in the notation. So later on we can be a little bit, we can be careless. So you have both choices. You can define it this way or the other way, but later on it will not matter, because you will be seeing that the stress tensor is symmetric. My purpose here for indicating the stress tensor components is really to identify the components in this matrix with a certain traction vector. And you could do the equivalent in the other notation. In that case, you would have the columns associated. Now let's look at an example which is very common. Let's look at pipe flow. We already calculated the strain tensor components today of pipe flow. How would we get the stress in the flowing material in the pipe? How would we do that? We would put in, we would mount, of course, a stress transducer into our equipment. Unfortunately, we can only mount a solid transducer at the wall. So here is a little transducer mounted. It has a membrane which separates the fluid in the pipe from the fluid in that transducer, and that fluid is expanding some cylinder when it's under pressure, and the cylinder expansion is measured with some strain gauges, and that gives us the pressure in that transducer. Now note, the only force which is transmitted here is a normal force. We cannot transmit a shear force. A shear force on that membrane is supported by the frame of that transducer, but it's not being transmitted to the interior liquid. So only the normal component of the traction is being transmitted to the fluid in here, and we would call the transmitted quantity the pressure in that transducer. So the pressure is equal to the traction times the normal vector. It's just the projection of the traction in normal direction. And the traction can be now defined in terms of n times the stress tensor. We would like to know the stress tensor component. That's why we are doing that. Actually, we would like to find out which component of the stress tensor are we measuring in this experiment here. Okay, so we express everything in terms of the stress tensor. N dotted into the stress tensor from both sides gives us a component in r direction here from this side and also from the other side. So we have pi rr, we have the r component of the stress tensor, evaluated at the wall. That's what I mean with W. So in our experiment, we have a stress tensor which has 9 components. Later on you will see it's symmetric, so we have 6 independent components. And out of these 6 components, the only information we gain in our transducer is the normal stress And we don't even have the field of normal stresses, we only have the normal stress at the wall. Now, how can you increase that information? You have to analyze the flow, you have to model the flow, and then you get information about the other stress components. So we will use a combination of measurement and analysis and modeling, and then find out about this. Okay, so far we described the stress in terms of attraction. Now, the traction is defined as n times the stress tensor, pi. If we change our normal, if we change our area element for which we calculate the traction, for a given stress tensor pi, let's assume that at point P we know the stress tensor. Okay, we have all the components of the stress tensor. Now, what would the traction tensor, what would the traction vector do as we change n? And it turns out that the tip of this traction vector moves around an ellipsoid, the so-called stress ellipsoid. And this ellipsoid has a longest axis. This would be the largest principal stress. It has an intermediate and a shorter axis, and those are the three principal stresses we would determine this way. And those principal stresses are in right angles to each other. And the direction of the ellipsoid here, given here, would give us the principal axis of the coordinate system of the stress. So we can analyze the stress in terms of its principal stresses. Next time I will come back to this point. We will continue working with the principal stresses and relating that to the other properties of the stress tensor.